while you guys were working, I made a little animation in Desmos, as one is wont to do. So here's the Desmos.
Why does it feel so dead?
Okay, are you guys ready for the amazing math animation of this function? So it's if you're between n and n plus 1, it's 1, and then otherwise it's 0. So you have like a little bump. So we can zoom in a little bit to make it look a little better. Where is my mouse? Here's my mouse. Okay, let's zoom in. Okay, there's your little slidey 1. So you're 1. Right now, n is what? 2. So between 2 and 3, you're 1. And if I animate n, let's animate only going up, because that's what things happen. Then it just slides over. Okay, it slides over. So this is a variation on the example we've seen like 5 times now. It's some kind of sliding box. But as you've seen, the sliding boxes can be quite tricky. So what's going on with this one? And the question is it converging almost everywhere? Is it converging in norm? What is it doing? I guess n should start at 0 or something, or 1. Let's start at 1. Let's go up to 20. 1 to 20. And then go like that. So when we do sequences, of course, in real life it's discrete, right? It can't be like a decimal, but nice animation. Okay.
You can do actually click on the slider thing.
Oh, you can? I know you can make it
step.
You can do this to make
there.
it step.
Not there, no. It's on the bounds. Click on the bounds.
Ah, yes. Okay, step 1. Let's make step 1. All right. Let's do it. Sure. But now it looks lame. Now it looks like it's lagging. That's not what I wanted.
Well,
anyway, that is closer to reality. Okay. In any case, you get the idea. It's a step function. Okay. What did you say? Is it converging in almost everywhere? Is it converging in norm? Let's see. What did people say? Okay. Okay. So 6 people answered. We got a 2-1-3 split. 3 people are in. Does not. The almost everywhere limit does not exist. And the L1 norm limit is 4 people said does not exist. 2 people said 1. I will tell you, the L1 norm limit does not exist. So 4 people got that right. The L1 norm limit does not exist. If the L1 norm limit existed, there would be some function where the difference between fn and that function is going to 0. So you gotta be careful here. Like 1, when you type in 1, you might think it was 1 the number, but that's 1 the function, right? Talking about L1 norm convergence, we're talking about limits of functions. So is it getting close to the function 1? Well, you would plot the function y equals 1, and that's that green function. It's not getting close to that function because the difference is always this big chunky region over here. So it's definitely not getting close to that. And in fact, it never converges to anything because it's sort of integral. The integral of fn is always 1, right? For every fixed n, the integral is always 1, and there's no way to sort of catch it with just one simple function, right? It's like whatever function you think it's going to converge to, it's going to eventually move past that function. It's not going to be getting close to that thing in norm. We'll have more to say about this as well when we figure out what the answer to the almost everywhere limit is. So obviously, people are all over the place over here. I'll reveal it does not exist is the wrong answer. So in almost everywhere, the answer is does not exist, is something else. So I'll let you think for a second. We'll re-vote and see if you can think of what your mistake was. Remember, try to imagine that you're a little point and you're sitting here. You're the point 7, 0, and you're sitting here and you're asking, what is the sequence of functions doing? What is the sequence of functions doing? Right? Almost everywhere convergence means at every single point or most points, what's going on? All right. Okay, I'm going to re-vote it and open it up for another minute. No, real numbers, no shenanigans with made up numbers. Real numbers.
Those are real numbers. Well, I think even the extended real numbers doesn't work because you're getting infinity. That's why I was thinking. That is the case. If it is not infinity.
So the thing is, you can make the extended real numbers, and then you can talk about limits of numbers. That's like kind of reasonable. If you talk about functions on the extended real numbers, it doesn't really work. Like I'm sure you can like torture it and make it something, but like it's quite tricky. So yeah, the regular x is an honest real number, hardworking real number, and
then it has to be
there's no tricks. Okay, I'm gonna stop it. I got 5 answers. That was what we had last time. I'm gonna stop it. I don't know who number 6 is.
It's a good thing.
I'm just gonna do it. Okay, I'm doing it. Nobody's taking any drastic action. Oh, there we go. Okay, great. Okay. Perfect timing. Okay, so this time, 5 people now think the almost everywhere limit is 0. Remember, it's not the 0 of the number, it's 0 of the function, right? So like, if I was nicer, I would have put a vector 0, because I'm talking about the function that is 0 everywhere. The function y equals 0. Y equals 0. Where's y equals 0? Right here. So, is it converging almost everywhere? So for which points is the sequence of blue functions that you can barely see now, where are they converging to the red ones? Of course, they're not equal. It's never equal to the red one. But for every fixed point, if you're some point living on the real number line, eventually the spike passes you, and then after that point, you're always equal to 0. So just like some of our other spike examples, as soon as the spike passes you, you are equal to the limit, which is 0. So you guys got that right? It is indeed, the limit is 0 in almost everywhere, and the L1 norm limit does not exist. So the L1 norm limit does not exist. There is no function that gets close to a norm, because the integral is always 1. But there is a function that gets close to for every point, because eventually the spike passes you. And this is, I guess, the third in our installment of tricky sliding spikes. In all the other ones, we were looking on 0, 1. This is the first example where we've seen the other type of infinity, where the sort of mass of the function is running off to infinity. So on 0, 1, tricky things can happen with like the spike going up to infinity, or like the spike moving over top of itself like infinitely often. But in this situation, we sort of have a mass of 1 moving off to infinity. And you can see that actually the integral of the function, the integral of the fn's is always 1, and the integral of the almost everywhere limit is 0. Some of the mass was sort of lost at infinity. The integral sort of disappeared at infinity in the limit, and you can see exactly how it got carried off, right? It got taken away on a little train going to infinity. Yeah?
So the set x between n and n plus 1 becomes a null set when n goes to infinity?
No, it's not that it becomes a null set. For every fixed n, it's a null set. Or sorry, for every fixed n, it's an ordinary, honest-to-goodness set of measure 1. Like the integral of the function is always 1. It's just that the problem is the sets, they never settle down. They keep moving and moving, and they will disappear. If you tried to arrange an example like this on a bounded interval, then by the compactness of the bounded interval, no matter how you did it, eventually it would have to cover itself many times, right? So there's something special about the real number line, which is that you can escape off to positive infinity and sort of never come back to the numbers you were at. Whereas if you're on a bounded interval, you come back over and over again if you try to do some infinity shenanigan. So this one we haven't seen yet, and I'm warming you up because later we're going to see a theorem that helps you rule out this kind of thing. So when can you sort of police the functions and make sure that there's no escaping mass? We're going to see a theorem that does that, which we might get to today. So a good example on almost everywhere versus convergence of norm, which is sort of the topic this week. Any questions or comments about that example? Yeah?
This is kind of what Jayu just asked, but in the definition,
Yeah.
it said that the limit as n goes to infinity where the fn's aren't equal to the f is null.
Uh-huh.
And I guess I'm not seeing how, as n gets really big,
Yeah.
I still see that there's a problem.
In this situation, it's not only a null set, it's literally everywhere, right? So for which value of x? Yeah, let's write it down. Maybe I said it too quickly. Let's
Oh, I see, because you pin down the x first.
Yeah, exactly. So it really has to do with the order. So for every fixed x, the fn of x, it's equal to 0. I could say eventually, but I could be even more precise and say for n greater than x. So as soon as n is bigger than x, then fn of x equals 0, always, which is what we're defining this limit to be, f equals f of x. So So the limit as n goes to infinity of fn of x equals f of x, which is 0 for every, I should say for every x first. Let's do that to be crystal clear with that. So in R, this is true. And so this is not only almost everywhere convergence, this is everywhere convergence. Almost everywhere convergence would say, okay, it's true except for when x is irrational or something like that. It would still be good enough. Yeah.
So how is it for every x in R if it's for every x less than n? How can it be for all the x's in the range if it's...
So because the limit as n goes to infinity only cares about large values, right? So what happens for the first 1,000 fn's doesn't matter. In the limit, we only care about what happens eventually, and eventually it's equal to 0. Like if you wanted to give an epsilon delta proof, you could say, given any epsilon, I will choose n naught to be x.
Like basically you can always pick an n that's bigger than x.
Exactly, right, that's right. Yeah, so it's kind of a tricky one because normally you don't actually reach your limit, right?
Sure, yeah.
Normally you just get closer and closer to the limit, but this is a situation where not only do you get closer and closer to the limit, you literally hit the limit at some point and you just stay there forever. So it's like some kind of super convergence. Yeah. Great question. Anyone else? Okay, so great example of almost everywhere versus in norm convergence. You've seen all the things that can happen. Basically everything, if almost everywhere in norm don't agree, it has to be something like we've seen before. So either a box going off to infinity this way, a box going to infinity vertically we've seen, right, where the spike gets taller and taller, or this like sliding box that like goes over top of itself a bunch of times. That's one where it can go to 0 in norm, but not almost everywhere, if the box touches every point infinitely often. That was the example from the textbook last class. Okay, so yeah, we're basically today, what we want to do is, first of all, finish our proof of that we were in the middle of last time, but we're essentially doing more theorems that relate convergence in norm to convergence almost everywhere. Okay, and I'm looking for the thing, probably it was some previous date. Let's try February 9th. No. 8th? No.
You're in topics there.
Oh yeah, this is the Belmont quiz. Yeah, let me see, maybe it's this one? Well, I don't know. We'll just start a new one, okay? I definitely should learn to be more organized, but alas, I am not. Okay.
Why is it called 1030 instead of topics?
Yeah, again, because I taught this course, Math 1030, I taught that like 2 years ago, and I never made a new folder, and now we're just in the folder. Okay, so guys, no making fun of me. Okay, okay, so we were in the middle. We were in the middle of proving exactly one of these theorems, and the theorem says that if you have this absolute summability condition, that will save you, and nothing bad will happen to you if you have the absolute summability condition. So if the sum of the absolute value of the integrals with, let me make sure I get this right. The integral of the absolute values is less than infinity. So this is a sum of a bunch of numbers, right? So every single function has an absolute value, you integrate it, you get a number, you add up the infinite sequence of these positive numbers. If that's absolutely summable, less than infinity, then there's no almost everywhere in norm shenanigans, right? Then the limit as k goes to infinity of the sum of the fk's almost everywhere, let me write it like this, almost everywhere exists, and it's equal to the limit, okay, I'm mixing up my n's and my k's here. N, k equals 1 to n, the limit as n goes to infinity of the sum from k equals 1 to n of fk in norm exists, and they are equal. Both, let's say they're both equal. Both equal. And we were proving a version of this where we said, if you call this thing f, then the f is the almost everywhere limit if and only if f is the norm limit. So we were actually proving theorem 2.7.12, which says that, I'm going to call a star to save a little bit of space, under absolutely summability condition star. So you have the summability condition, then f is the almost everywhere limit if and only if f is and only if f is the in norm limit. They're both the same. So you can't have these weirdo examples that I keep throwing at you guys. They cannot happen as long as you have this absolutely summability condition star. That thing will protect you. And if you look at the example we just did, the warm-up problem, why don't we have that? Well, if you try to add these up, the norm of each function is 1. If you wanted to make it into a sum, you would have to like subtract off the previous function. So this is not exactly the setup of the theorem. The setup of the theorem says you're adding up a sequence of stuff. So to add things up to get this, you have to do like plus this minus the previous one. So you get one of those like spiky functions like this. In the example, you would get a function that looks like this. You subtract off the previous spike and add the next spike. And if you took the norm of that, it's 2. So the sequence of the fk's, their absolute value is 2. Or the integral of the absolute value is 2. And of course the sum of 2 plus 2 plus 2 plus 2 forever is not less than infinity. That's why it's possible for us to have a bad time in this situation. If you actually had it being summable, then things would be fine. Okay, that's where we were. And I think we even proved one way. So we were proof. We did one direction. Next up, we'll do the Spice Girls. Okay. What did we do? We did implies. So we said if f is the almost everywhere norm, then if f is the almost everywhere limit, then f must be the limit in norm. And the way we proved it is we found a function g, which was the almost everywhere limit, and g is the limit in norm. So we had this g, and this all came from because of star, and all our theorems that we've proven, we found this function g, which is both the almost everywhere limit and the limit in norm. We proved one direction, that if it's the almost everywhere limit, then it must be the limit in norm. That was last class. And right at the beginning of today, I will do the reverse, which is if the sum goes to f in norm, then f is the almost everywhere limit too. Okay, so that's all sort of recap. That's what I'm about to prove. But let me know if there's something I should further recap to make it make sense. Okay, so the first claim, f is the limit in norm. G was also the limit in norm. And I claim that the integral, the distance, the L1 distance between f and g, also known as the integral of f minus g, I claim that this is 0. This equals 0. Why? Proof. It's just a nice little triangle inequality. F minus g is less than or equal to the integral of f minus the sum of the first n terms, no limits here. So for any n plus the integral of the sum of k equals 1 to n of fk minus g. This is by triangle inequality. Triangle inequality. And what do we know? We know that this thing is going to 0 because f is going to the sum in norm. So this thing goes to 0 since sum to f in norm. And this one also goes to 0 for a different reason, which is that the sum is going to g in norm. Okay. So for any n, the integral of f minus g is bounded by the sum of two things, both of which go to 0. So the whole thing altogether goes to 0. And therefore, it must be that the integral of f minus g equals 0. What number is less than two things going to 0? The only number is 0. If you wanted to do it epsilon delta, you would say given any epsilon, wait until this guy is less than epsilon over 2, wait until that guy is less than epsilon over 2, then this guy will be less than epsilon. Yeah?
Sorry, why does the sum converge to G in norm?
Why does which one?
The sum converge to
Because we were proving that if f is the limit in norm, then it's the almost everywhere limit. So we're proving this direction. of the thing. So we're assuming this is our hypothesis, and this is our conclusion. So we're saying, given that the sum converges in norm, we're going to prove that it converges almost everywhere. And converging in norm just means this goes to 0, right? This is the norm of f minus the sum from k equals 1 to n of fk. That's the norm, and we were given that this norm is going to 0.
I get that one.
Oh, the other one.
G.
The g. Okay, fantastic. Good. Very clear. The g was what we did last time, right? We found the function g, which was the almost everywhere limit and the limit in norm. I can tell you what g was.
So you're using one from the last.
This is the g we set up last class. And I didn't write down the definition of g, but I told you the two properties of g that are important. I can even give you the definition, which is g of x is equal either to 0 on the bad set, or it's equal to the sum when the sum makes sense and is absolutely summable.
Okay.
Yes. Okay. This is great. Great question. Okay. Yeah. Right. This is why it's sort of uncomfortable to stop halfway. I guess sometimes it happens. Okay. Great question. Anyone else? Okay. So if the norm of f minus g equals 0, then you'd be tempted to say f and g must be the same function, but that is not true. But what you can say is they are almost everywhere equal. And that is a theorem we did earlier. Therefore, f equals g almost everywhere. This is theorem 2.7.5. And this is one of those tricky theorems where we wrote the indicator function where f is not equal to g. We wrote it sim equal to f minus g plus f minus g plus f minus g plus f minus g. We wanted one of these like silly infinite sums that seems like it can't possibly be true because it's only true on a null set, a set of measures 0. Okay. So f equals g almost everywhere. G, on the other hand, is equal, since g equals the sum from k equals 1 to, let's say, the limit, n goes to infinity. I'm trying to be more careful about writing these sums as limits when they're functions, because then it really matters if you're talking about the almost everywhere limit or the in-norm limit. So I'm trying to remind us that there are always limits by writing the word limit almost everywhere. So because g is the almost everywhere limit and f equals g almost everywhere, we have, two things are equal to g almost everywhere. It could be a problem. You might say, oh, what if one almost everywhere isn't the same as the other almost everywhere? But we did this last class, where if two things, you have two null sets, you do this like intersection of the two sets, and everything will work out. So if g is something almost everywhere and f equals g almost everywhere, we have f equals the limit as n goes to infinity of the sum almost everywhere too. And you can say because f equals g almost everywhere. And so again, this is the thing that the union of two null sets is still a null set. That's the property being used. I think this has a name in the textbook that we skipped over, but we did the proof of it. So I didn't give it the name. And I didn't even write down the name. Oh, I did write down the name. Okay. Theorem 2.7.5, if you want to look in the book. 2.7.5. So that says that if you have two functions and they're equal almost everywhere, then they're equal to each other almost everywhere as well. Okay. And that's the proof. That's it. So basically we have this function g that is both limits, and any function f that is 1 must be also equal to g. Exactly. Questions about that one? Okay. So, like I said, we're going to continue with this. Now we're squarely in what is called chapter 2.8 of the book, which is on convergence theorems. And of course, we've just done a bunch of convergence theorems. So I think a more accurate title would have been more convergence theorems. But it's really like taking some of the things we've done and like souping them up into better and better versions of themselves, into situations you can use them more and more. And I came up with an example to help motivate us. Of course, like all my favorite examples, it comes from probability. So here is my sequence of functions. Let me draw it first. Let's draw it first. That'll be fun. So here's my sequence. So f1 is the function 0 to 1. So 0 to 1, f1 of x is equal to 1 in 0, 1 and 0 otherwise. Okay. Also known as the indicator of the set 0, 1. Very nice. function, that's f1. f2 is a little piece of cake on top of this guy. f2 is the indicator of 1/2 to 1. 1/2 to 1. f3 is the indicator of 3/4 to 1. And f4, I think you might spot the pattern, f4 is the indicator of 7/8 to 1, and so on. And when you add them together, you get this nice stack of cakes. So if you look at, let's call it the sum, Sn, which is the sum, it's going to be the sum from k equals 1 to n of fk. This has the property that its maximum height is n, and it's exactly this function with n layers of cake added on. And you can imagine as you add more and more layers, you go up, up, up. So there's as you add to infinity, this function gets taller and taller. Its maximum height is going to infinity. So that's the function Sn. And you might be worried about this function Sn, like, oh, like what's going on in the limit as n goes to infinity? Because again, you're adding up infinitely many things. So you should worry. You should be very worried. I will tell you Sn, like I said before, it has a nice probabilistic interpretation, which is Sn is the number of coin flips needed in the first n flips. Okay, let me say it this way. The number of coin flips until a heads comes up. Or n if no heads in first n coin flips. So like we were doing last class, you can think of the interval 0, 1 as actually being infinite sequence of coin flips. And Sn is the wait until the first heads random variable. So for some point Sn, let's do it. If x equals is tails, 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 heads, then Sn of x will be 1, 2, 3, 4 for n greater than or equal to 4. So it's kind of like how long you have to wait until a heads comes up, but we're truncating it. We're only going to look at the first n coin flips. And the thing is, you can't look at all infinitely many coin flips at once and have an honest to goodness function, because then the answer might be infinity. Like if you want to have a function that terminates at some point, you got to put a cap on it, like we did here. So that's the function Sn. This is a really well-known random variable. You might have heard of this. Does anyone know what it is?
The exponential.
Very close. It's the exponential's like pre-limit. If you take the limit of this guy, you get the exponential. The exponential is the continuous version of this thing. Yeah. What was that?
Is it the Poisson?
Not the Poisson. The Poisson is the continuous version of how many heads there are. So you guys are thinking of like these like continuous limits of these coin flip things. What was that? Binomial is exactly the number of heads. This is the time until the first head.
The geometric.
It's the geometric. Yeah, that's right. Good, you guessed the right buzzword. Geometric.
There's only so many.
And actually, more accurately, the geometric is not this. This is something you can define with n coin flips, right? You flip n coin flips. If the heads came up, you count how many it takes. If no heads come up, then the answer is n. You just say, I flipped all the coin flips, I got no heads, right? The geometric is not that. The geometric could be infinitely large. The geometric is the limit of this, is the limit as n goes to infinity of Sn. That's the limit. And here's the thing, right? You want to talk about the geometric random variable. It makes perfect sense. Like, let's flip coin flips until we get heads. It could take us 10,000 coin flips. That's fine. I don't want to pre-specify a thing. That's what the geometric is, and people talk about it all the time. But mathematically, this is like an infinite sum of these functions, right? And does it exist, right? Like, can you take this limit? And you can take the limit almost everywhere, because for any particular sequence, the probability of having infinitely many tails in a row is 0. So the almost everywhere limit is great. So this almost everywhere, yay. But is the limit? Could the limit be in L1? But does the L1 limit as n goes to infinity of Sn exist? Right? So we can take the almost everywhere limit. That's fine. That's no problem, because for any fixed sequence, this makes perfect sense. But can you make sense of this as a function? Like, can you do the integral or the expected value of this thing? And the answer in this case, if you look at the boxes and you think about the theorem we just proved, the theorem we just proved is actually powerful enough to handle this case. Because the theorem we just proved says the only thing you got to check is that absolute summability condition. And you must check, this is from the previous theorem, that the sum of the integral of the f k's is finite. So the sum of the integrals is exactly the sum of the areas of these boxes. This box has area 1, this box has area 1/2, this box has area 1/4, this box has area 1/8, and so on. So this condition of the integral of the individual pieces being summable is satisfied. It's 1/2 plus 1/4 plus 1/8 and so on. This whole infinite sum is the sum of 1 over 2 to the k, maybe 1 over 2 to the k minus 1, which adds up to 2, which is less than infinity. So the infinite sum, let's go to infinity instead of going to 2. So the previous theorem we did, that says that if you have all these little pieces and they add up, you get the thing. That works. That's a good enough theorem. We're going to just make better and better versions of this that are more and more useful, but I think this example is nice to keep in mind to see why it works. I think this is also a good example to notice the difference between the Lebesgue integral and the Riemann integral. So you're used to the Riemann integral where you do vertical slices. And if you tried to vertically slice this function, you would have a bad time. Because when you did a vertical slice near x equals 1, you would have an infinitely tall piece of pi to slice. And that would be a problem. But slicing horizontally as 1/2 plus 1/4 plus 1/8 and so on is working out perfectly fine. So this is a nice example. We'll keep this one in mind as we go and we see all the theorems. I will say on the topic of Riemann integration, someone told me that you guys never actually covered it in a previous course. There was one question on the assignment that had Riemann integration. I made that a bonus. So if you've never seen Riemann integration before, please feel free to skip that question or take a stab at it. Or if you want to go watch some video on Riemann integration and then try the bonus problem, that's fine. That's another good topic for the, if you want to do that for your final project, I'll let you do that as well. There's a nice section in the textbook actually on that reviews the Riemann integral and compares it to the Lebesgue integral. So also fine if you want to do that. Okay, questions about this example or like where we're going? Yeah.
This isn't actually about this example.
Sure.
It's just in the notes from a couple lectures ago, we wrote that convergence in norm implies that the integrals of the fm's go to the integral of f.
Right. Yeah.
The converse isn't true.
Right. Yeah. And I think you can go back to chapter 1 and think about that property. So the convergence in norm, in any type of norm, means that this integral, x minus xn, goes to 0. And x minus xn goes to 0 must imply that the norm of xn goes to the norm of x by some triangle inequality. Like you add it to both sides or something, like it's not that difficult. But the reverse is not true. So just because your norm is the same, your norm being the same as somebody else's norm means you guys are both at the same distance from the origin. Right? And of course, if you're the same distance from the origin, that doesn't mean you should be at the same point. The converse is of course true. If you guys are converging to the same point, then of course you will be the same distance from the origin.
Right.
Yeah.
Okay, thank you.
So it's kind of a general property, not just for integrals, but for any norm. Yeah. Great question. Anyone else? Okay. And yeah. So the first theorem we have actually does harken back to our chapter 1 days, which is we're going to prove that L1 is complete, right? Theorem, and it's going to be a very short proof because we've already done all the heavy lifting. Theorem, L1 is complete. That is, every Cauchy sequence converges, i.e. that's what complete means. Every Cauchy sequence converges. Okay. And the proof is going to be extremely short because we've already done it. So we're just repackaging a proof that we've already done. This has a name in the textbook, which is 2.8.1, theorem 2.8.1. Here's the proof. By chapter 1 stuff, it suffices to show every absolutely summable sequence converges. This was in chapter 1. Do I even have the name in chapter 1? I did not write it down. I just said it suffices. Okay, so this was something we proved in chapter 1. So if you want to prove it's complete, you just got to look at sequences where the sum of the norms of the xn's, if that is finite, that implies the sum of the xn's converges in norm. This is what we proved last time. N going from 1 to infinity, and n going from 1 to infinity. But of course, we're working in L1. We're doing the L1 norm. So why don't, instead of writing xn's, let's write f's, right? The norm of fn, and that's going to be the L1 norm, that means the fn's converge in norm. So if you have a sequence of fn's that are L1 convergent, then their sum, their infinite sum, must converge. That was the proof we just did. This was the previous proof. Theorem. So theorem 2.7 whatever that we just did. 2.7.12. So basically, being a Cauchy sequence, it suffices to look at these absolutely summable sequences, and those are exactly the ones where we have all the nice conditions, and we know there's an almost everywhere limit and a norm limit. And so that proves that it's a complete space whenever you have this absolutely summable thing. Everything is nice, everything converges nicely. And you can look at the picture. The reason I drew the picture is this is an example of one of these absolutely summable series, right? Adding up little boxes, as long as the sort of the size of each box is getting smaller and smaller in a summable way, the limit will exist and will be some actual function in L1 at the end of the day. Okay, so very easy proof because we did all the hard work already over the last 2 weeks. We've been sweating to do it, and now we finally have it. This is the big upgrade over the Riemann integral, right? The Riemann integral is not complete. With completeness, we can talk about Fourier series and stuff like that. That's how all this stuff works. Okay. The next little convergence theorem that we have is a nice relationship between almost everywhere and in norm, right? In almost everywhere and in norm, if you don't have the nice summability condition, they're not related. You have things both ways, but there is something interesting between them, and that is the next theorem. And the theorem says, what number is this? Oh. Where is this theorem? But I have the proof of the theorem written down. I just don't have the statement of it. Okay, yeah, here it is. 7.8.2, the next theorem. 2.8.2, thank you. Yeah, it's in chapter 7. Okay, theorem 2.8.2. If fn goes to f in norm, so you have convergence in norm, then what? We would like to say, it would be great if fn goes to f almost everywhere, but that simply is not true. But what is true is you can always find a subsequence so that it does converge. Then there exists a subsequence. I'm going to call it Pn to match the textbook notation, so that fPn goes to f almost everywhere. So it's not true that the fn's will go to f almost everywhere, but some subsequence of them will converge almost everywhere. And if you want to think about an example, I think you can think about that sliding box example on 0, 1, where the boxes were kind of sliding and getting thinner. In that situation, of course, for any given point, it doesn't go to 0 because you're covered infinitely often by 0s and 1s as the boxes slide over you. But of course, you can take a subsequence where the boxes don't slide over you, right? Just take the subsequence of 0 to a half, 0 to a quarter, 0 to an eighth, and that is converging to 0 almost everywhere. So some subsequence is converging to 0. The theorem says it will always happen. Okay, and how does the proof go? Before I give you the proof, let me sketch an idea of the proof. And again, this is using an idea we've seen before, which is writing the conversion between limits and limits of sums. This telescoping sum idea, where you convert from some kind of limit to some kind of limit of sums. So instead of looking at f on its own, I'm going to think of fn, I'm going to write it as f1 plus f2 minus f1 plus f3 minus f2 plus and so on, plus dot dot dot, plus fn minus fn minus 1. So instead of just thinking of fn on its own, I'm thinking of it as a telescoping sum of these differences being the thing that matters. And then if you take the limit, you'll see that the f, which is the limit in norm of the fn, so the norm limit in norm, is equal to the limit, n goes to infinity, of f1 plus f2 minus f1 plus dot 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 dot. Okay, why does this help us? I guess, yeah, let me not write a last term. There is no last term. It goes to forever. Okay, great. Why does this help us to think about it as a sum? The reason it helps us to think about it as a sum is we know that if the sum was absolutely summable, then we would have superpowers, and the convergence and norm would be a convergence almost everywhere. So, like, it would be so nice if we could just put norms on everything. If we put norms on everything, we'd have the norm of f1. This is like our dream. How do I draw a dream? Here's me asleep, and then I'm dreaming. Okay, this is my dream. I have the norm of f1 plus the norm of f2 minus f1 plus the norm of f3 minus f2 plus dot 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 dot. And if this was absolutely summable, then I would be in business, right? Then it would be, I could say, I could do this a number of ways now. I could apply the theorem from chapter 7, or I could just say L1 is complete. This is an absolutely summable sequence, and therefore by the completeness of L1, there is a limit. And we know when we have this superpower by the theorem we did before that it's in almost everywhere and in norm limit. If summable would be done. I guess let me put the exact thing. I think we technically do have to use the section 7 one, 2.7.12, right? And that one said that if you have absolute summability, almost everywhere and in norm are the same. Okay, but unfortunately, we're not in dreamland, and you can't always do this, right? You can't just like look at these. These differences might always be like 1 or something, or there might be so many of them that they swamp and they just blow up to infinity. So there's no reason they should be summable. But here's the thing you can do. When you're doing a telescoping sum, nobody says you have to do f2 minus f1 directly. You could do f100 minus f1, and then you could do like f1000 minus f100, f10,000 minus f1000, and we did this before. So the idea is, let's thin this down. This is all great, and only if this was summable, it would work. Let's not look at all the f's. Let's look at just a subsequence, right? So we're allowed to thin this out. Take a subsequence. Take a subsequence Pn, and do that as a telescoping sum. So f is the limit as n goes to infinity of fpn, right? So for any subsequence, a limit in norm, the subsequence will also converge in norm. And then you write this one, so you do f1 minus fp1 minus f1. Let's call 1 p0. Let's make it so p0 is 1. p0. Then there's a little more symmetry. Plus this, plus fp2 minus fp1 plus dot dot dot. And so I thinned out to a subsequence. Now, maybe my dream will come true because I'm the one who's in charge of choosing the subsequence. If I choose the subsequence correctly, maybe I can make it so fp1 minus fp0 is small. Make them small. So here's this dream. This dream was a bust, but this dream has a chance. I don't know, I woke up for this one and I'm happy and excited. Okay, big speech bubble. So this one will work because I have the power to choose these FPs. And I'm going to choose them. I'm going to make sure I can ensure all terms are summable. I'll call them summably small. That's so small they are summable by choosing Pn. So that's the idea. We're going to make this thing work by choosing the subsequence so that all of these differences are super small, and then everything will work out. Of course, this is all just the sketch of the proof. I'm going to give you the real proof now. This is all just to set up the idea, so it doesn't seem like it comes out of nowhere. But now that you know the idea, I think it's not too hard to fill in the details. The hard part is coming up with this idea. Questions here before we jump into the nitty-gritty? Yeah.
So when we start the sketch,
Yeah.
you would just define the f to be f1 plus f2 minus f1.
That's right. So I'm using the fact that Fn is this telescoping sum, right? And the reason it's this telescoping sum is because like everything cancels, right? Like F1 cancels with F1, you're left with F2, cancels with F2, and so on. So it's just like a fact about addition. Yeah. Are you asking why it's true? Or?
So is Fn like still a step function?
No, in this situation, Fn is any integrable function. Yeah. Other questions? Okay, so here's the actual proof. And here's what we do. Since the integral of Fn minus f goes to 0, let Pn be such that the integral of Fpn minus f is less than 1 over 2 to the n. So this 1 over 2 to the n is eventually going to be the thing that makes our sequence summable. Of course, you could replace the 1 over 2 to the n with your favorite summable sequence, but my favorite summable sequence is 1 over 2 to the n. So because it's going to 0, it's eventually less than any number. Just take the sequence, so that's less than 1 over 2 to the n. If you wanted, you could say set epsilon equal to 1 over 2 to the n to make it extra crystal clear. Let's do it. Set epsilon equals 1 over 2 to the n to get. Okay. Now here's the claim. If you do, the norm of Fpn plus 1 minus f of Pn, why am I all of a sudden thinking about this? Who cares about this? Well, the reason is I already had my dream, and I know that that's the thing I got to do. So here we go. Fpn plus 1 minus Fpn, that's the integral of Fpn plus 1 minus Fpn, which is the less than or equal to the integral of Fpn plus 1 minus f plus the integral of Fpn minus f. Let me write it the other way to make the triangle inequality more transparent. F minus Fpn. Okay. Essentially what we're doing here, these two things, if the Fpn's are close to f, then the Fpn plus 1 has to be close to Fpn because they're both close to f, right? So triangle inequality, how far away could it be? Well, if they're both close, then, you know, worst case isn't too bad. This one is less than or equal to 1 over 2 to the n plus 1. This one is less than 1 over 2 to the n. And that's an addition I can do. That's equal to 3 parts over 2 to the n plus 1. Because this one is like 2 parts. 2 over 2 to the n plus 1. 2 plus 1 is 3, giving that. Okay. So by choosing it in this way, I made it so this thing is less than 3 over 2 to the n plus 1. And now I can take the limit. I say, notice the sum k equals 1 to infinity of the norm fpk plus 1 minus fpk. I guess it's 3 or something like that. Should I say what it is? That starts with, the first term is 3/4. So 3/4 plus 3/8. So you start with a quarter, so you get a half. Okay, 3 halves. 3 halves. Which is less than infinity. If you don't want to know what the sum is, all you need to know is that it's less than infinity. Because it's a sum, it's everyone's favorite infinite sum, a half plus a quarter plus an eighth. You just multiplied everything by 3 halves to begin with. And so, by theorem 2.7.12, that theorem we just proved at the end, we have that the limit as n goes to infinity of the sum from k equals 1 to n of fpk plus 1 minus fpk. This limit, let's say, exists almost everywhere and in norm. Right? So we have our superpower, absolutely summable sequence. This exists and it is equal to norm. And this sum, the sum from k equals 1 to n, fpk plus 1 minus fpk, that is exactly what I wrote in the dream, right? It's fp0 plus fp1 minus fp0 plus fp2 minus fp1. That's exactly fpk. So this is equal to the limit as n goes to infinity of fpn, right? So you add up these things, you subtract them, you get fpn. Okay, so that limit exists almost everywhere and in norm. Because it exists in norm, the limit must be f, since the limit as n goes to infinity of fn equals f in norm. So the limit of this thing exists almost everywhere and in norm for one function, and we know the limit of the entire sequence was f in norm, and therefore the thing that it must be over here must be f. Okay. So I'll just stop there. Okay. Let me know if you guys want more detail on the last step. I think it's clear. If you wanted, you could give this thing a name and then argue that whatever you named this thing is equal to f. But hopefully it's clear enough. Yeah.
When we selected this subsequence by setting epsilon,
Yes.
could we essentially just take all of the terms beyond a certain n, where that holds where the integral of the f
Yeah.
minus
If you like Pn is equal to the capital N you get when epsilon equals 1 over 2 to the n. The only other thing you have to do is make sure that the sequence that somebody gave you was increasing. Because like in principle they could just like throw out random numbers and they could go
so
down.
long.
Yeah. This is one of those details where if you start to write down exactly what you do, it takes you forever and you haven't like made it more clear. You've made it less clear by like putting all these like weird conditions like make sure that Pn plus 1. So it's if you can make it in a way that's not hiding too much, it's nice to say things like let Pn be such that blah, and then give some like little detail of like what is the actual like technical hardness thing that has to be done. Yeah, great question. Okay, so there we go. We have this almost everywhere convergence. The next convergence theorem, I think, will be the last one for today, is a really nice one. It is called the monotone convergence theorem. The monotone convergence theorem. What was the question? Oh, no question. Okay. And you have to be careful. There's a monotone convergence theorem for points in R, right? If you have a bunch of real numbered points and they're increasing, then they have to have a limit. That's not the one we're talking about. This is the monotone convergence theorem for L1 functions. And it says if the functions f are monotone increasing, so they're going up, then they're going to have a nice limit. So here's the if part. And this is theorem 2.8.3. Okay, so suppose fn of x increasing. Okay, I should say weakly increasing. The textbook, of course, says non-decreasing, which I can't get my head around. Weakly increasing, which means fn plus 1 of x greater than or equal to fn of x for all x. That's one condition. So they're going up. It could be flat. That's why it's weakly, but they're going up. Suppose they all have to be positive as well. Fn of x greater than or equal to 0 for all x. And there's one last condition. In the ordinary monotone convergence theorem for numbers, you need to have an upper bound, right? So they're going up, 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 but you need like some brick wall that stops them from crashing into something. And in the version for L1, that wall is this condition. The sup over n of the absolute value of the integral of fn has to be less than some n for some n. So the integrals can't be getting bigger and bigger, right? The f's, they're going up, 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 but their integrals, they only get as large as some capital M. Right? Of course, because the f's are going up, their integrals are also getting bigger and bigger. But there is some stop. They can't just get bigger forever and ever. What's the conclusion? These are a bunch of functions. They're going up, up. The conclusion is there must be something they converge to, both in norm and in almost everywhere. So then limit as n goes to infinity of fn exists both in norm and in L1 norm, and almost everywhere. Let's say in L1 norm and almost everywhere. Okay.
Just like
Yes.
where the limit has to be in L1 as well, right?
Yes. Right. If the limit exists in the L1 norm, then the limit is in L1. Yeah. Yeah, that's a good point. Okay. Before I prove it, the proof is again, it's going to be really short because we already have done everything. Like it's going to be a snap. We've done all the hard work already, and now it's just a quick one. We're just going to rewrite it in terms of our absolute summability condition. But I want to give you an example of where this is, what this looks like, and it goes back to our little stacked boxes geometric random variable example. So in this one, I called the fn's the little pieces, but let's give it another name. Let's call it I guess let's call it S for sum. If you call Sn the sum of the first couple pieces, k equals 1 to n of fk, right? So this is S1, S2 is like this, S3 is like this, right? So then the S's are going up, up, up. They're always positive. They're going up. What is their integral? Someone would ask you to calculate the integral of the Sn, and you would find that that's actually the partial sum of the sequence we calculated, 1 over 2 to the k plus 1. And that sum is always less than 2. Okay, yeah, that sum is always less than 2. And so, because of that, the monotone convergence theorem would say this converges to something. So, for sequences like this, you can do it by saying it's a Cauchy sequence, you can do it by applying our theorem directly, or you can do it by the monotone convergence theorem. They're all saying kind of the same thing. And the monotone convergence theorem is basically just like some convenient way where if the functions are increasing, you just like automatically know, you can like skip checking some conditions. Okay? Yeah.
Sorry, are you saying that each box is an S?
I'm saying S is the sum of the first n boxes.
Oh, okay.
So like S1 is the first box, but S2 is the blue box plus the purple box.
Oh, okay, yeah.
Yeah. Which is like really the function we want, right? Yeah.
Does it goes the same way when it's monotone?
Yeah, this is a good point. There's another version where it's going down. This is the monotone up convergence theorem. There's also the monotone down convergence theorem, where you would replace increasing with decreasing and greater than or equal to 0 with less than 0. So if they're going down to something, that's fine too. Yeah. In fact, in the textbook, they define what it means to be, I think they just say monotone. They say, what does it mean to be monotone? It means either monotone increasing or monotone decreasing. And then they prove it for monotone. But it's just no one, and then the other one is a minus sign away. Yeah. Good point. Okay, so like I said, the proof is a nothing burger because Fn, again, you write it as the telescoping sum, F1 plus F2 minus F1 plus F3 minus F2 plus F4 minus F3. Okay, and there you are sitting in the fields dreaming about what would happen. This is you. What would happen? Could it be that these things are summable? You're like thinking about the sum of all the norms. If the sum of all the norms was finite, we would be so happy. But actually, because they're monotone, what is the sum of the norms? The sum of the norms is actually just the norm of Fn. Okay, and the reason is the sum of the norms. Let me just write it out for you. So your dream does come true. It comes true. It comes true. If you just write it out, you'll see exactly what's going on. Because things are monotone increasing, the function f2 minus 1 is always positive. So when you take its absolute value to do the integral, you've done nothing. You've taken the absolute value of a function that was already positive. When you take the absolute value of this one, you've done nothing. All of these terms, because they're positive, they just add together. There's no triangle inequality, it's triangle equality. Everything is lining up. So let me write it out for you, and you'll see. So f is f1 plus f2 minus f1, and so on. And actually, if you take the absolute value of fn is the absolute value of f1 plus f2 minus f1 plus dot 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 plus f4 minus f3. I guess I should right, plus dot 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 all the way up to the last term, which is fn minus 1. So you take the absolute value of both sides. Now normally you would have triangle inequality and you would say it's less than some big sum. But this is not triangle inequality. This is triangle equality. f1 plus f2 minus f1 plus dot 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 plus fn minus 1. Why is that true? Why is it true that in this situation it's triangle equality? Because every single term is positive. When you take positive numbers, absolute value doesn't do anything. So because all terms are positive, so these terms are positive by weakly increasing. This is positive by weakly increasing, and f1 is positive by the greater than or equal to 0 condition. So the two conditions we put on the thing, that they're weakly increasing and that they're greater than 0, then that just means every single term is positive. Yeah. Okay. This is a good. It occurs to me. I think there's a really good comic for this. I think I put it in the folder, so I have to show you guys now if you haven't seen it yet.
More book comics.
Let me see if I can find it quickly. Content, comics. Yeah. Okay, it's right here. Okay, I'm very excited. Okay, this comic says it's a bunch of triangles, and they're protesting. The triangle equality now. Know your rights, right? Triangle inequality is a terrible oppression on the triangles. These people are protesting for a better life, and we have given them the better life in the proof of the monotone convergence theorem. Okay, so it's an equality because it's triangle equality, right? When you're adding up positive things, it's positive, and this works for every x, right? So for every single x, you could put in an x here if you want. Works for all x. I'll just say. Okay, and if this works for all x, you can find the integral. The integral of fn is equal to the integral of f1 plus the integral of f2 minus f1 plus dot 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 plus the integral of fn minus 1. Right? Both the left hand side and the right hand side are equal. So sum of finitely many things, you add up the integrals. Question? Yeah.
Yeah, if all the terms are positive, then what purpose do the absolute values still serve? Like, why do we leave them there?
Oh, because the theorem was stated in terms of if you have a...
Okay.
Right. So we're trying to match the thing so we can plug it into the
Okay,
next
so
thing.
they're just not doing anything.
Yeah, absolutely. Yeah, I totally agree with you. Yeah, we're trying to convince the reader of the proof that the sequence of things is going to have the sum of the integrals is finite, so that we can apply the theorem that says that means we have 0 powers. Yeah. Yeah. Okay. So that's true. So what can we say about the? Let's take the soup. Right. This is an infinite sum. What if we do the sum? This is the sum from k equals 1 to n of the integral of the fk plus 1 minus the fk. And let's take the soup over n. The soup over n. Well, that would be the same thing as the soup over n of the fn's. If you're doing the soup of an infinite sum and all the things you're summing up, the soup is like the biggest possible thing. Well, the biggest possible thing when you're adding up positive things is to add all of them up. This would be exactly the infinite sum. The sum from k equals 1 to infinity of the fk plus 1's minus fk. Right? So the biggest possible, if you're adding up more and more, you might as well add up infinitely many of them. And we were told in the hypothesis of the problem, the soup of this stuff is less than m. So m is bigger than this by hypothesis on m. Right? That was given bullet point number 3. The soup of the fn's is less than m. Okay. So what we've shown is that the integrals of the absolute values of the differences is finite. And so you can say by theorem 2.7.12, our superpower theorem, since the sum from k equals 1 to infinity of fk plus 1 minus fk is less than m, is finite. Therefore, the limit of the sum, n goes to infinity, sum from k equals 1 to n of fk plus 1 minus fk exists in norm and almost everywhere. Okay, but this sum is exactly the sum of the differences. This is the telescoping sum. This is our dream come true, that this is the limit of the fn's. And then we're done. So we basically just had to look at the differences rather than looking at the actual functions, and everything falls into place. Okay. That's the proof of the monotone convergence theorem, which is a really common theorem people use for these things. Questions or comments about the monotone convergence theorem or anything else? Okay, this is a good place to stop. Let's stop here, and we'll pick it up after the break in a week. Your homework is due the Monday after we get back. It does involve some things with norm, and almost everywhere, hopefully you've seen enough practice now, and as well as some kind of like hands-on calculations with simple functions and stuff. There's no simple functions in this course. Step functions, I shouldn't say. Simple functions is something else. Step functions. So yeah, please feel free to post on Campus Wire if you have questions and to get your marks back for assignment 1. Yeah.
Is there any chance you can do like a Zoom office next week?
Yeah, if you want to meet sometime, I'm pretty free, especially towards the end of the week. So just send me a message and I can set something up. Yeah.
Great, thanks.